Thanks to the organizers for putting together a great program. You guys having fun? Can you hear me? All right, awesome. Well, this is a conference in honor of Boss Eixhoven, so I agree with Samuela that he would not want us to be sentimental, but I hope it's okay if I say a few words. I was a graduate student at Berkeley of Lenstra, and I visited him in Leiden for part of my PhD studies, and that's where I first met Boss Eixhoven. So my first impression of him was totally intimidated. Am I the only one who has had that impression? Okay. I'm sorry? Well, I don't know. I was at that stage in my graduate career where somehow the more math I learned, the more I felt that I was understanding less. Maybe that never goes away. I still feel that way. But anyway, that didn't help to, maybe that's just how math goes. But I mustered up the courage and approached Boss and asked him about M111 and delta. And that hour conversation in his office really left a profound impression on me. I'm not sure that I followed everything. I'm still have the sheets, and I look back on them, and I wonder if now I'm going to understand everything that he was trying to communicate to me. But what it left was like he was a master of the abstract and the concrete in equal measure. And I still somehow, I can only be an apprentice of the master, if that makes sense, but I still try to carry on his tradition of mathematics, somehow to celebrate the computational and the functorial and how they go together. So that's inspired how I do mathematics, and I hope to carry on his spirit in that way. On that note, I'd like to tell you about a family of Jacobians with definite quaternionic multiplication. This is joint work with Victoria Cantarell-Farfan and Davide Lombardo. And the theme of the talk really is using computation to inform theory. And our broad goal is to understand explicitly the images of Galois representations coming from abelian varieties. So I got to set up some notation for you. I think I'm going to lead with the theoretical question and then show how some explicit families and doing some computations with them sort of provides an answer to the theoretical question. Okay, so notation. So F will be a number field. We'll take its Galois group, absolute Galois group, to be gal F. F-al will be an algebraic closure of F. Let A be an abelian variety. Over F. Maybe we'll let G be its dimension. Okay. And boy, wouldn't it be great to understand abelian varieties? Okay, so that's too hard. So the first thing we do is to try to answer or understand our abelian variety through linear algebra. And that means replace A with its Tate module. So we choose a prime L. We let TLA be the limit of the L to the N torsion. It's a free ZL module of rank 2G. The best part about this is that it carries an action by the absolute Galois group of F, and therefore it gives a representation rho AL from gal F into the ZL linear automorphisms of the Tate module, which as a group is isomorphic to GL2G of ZL. And the defining property is that the determinant of 1 minus apply rho to the Frobenius so this is LP of t. It's a polynomial with integer coefficients that starts out with a 1 This is the numerator of the zeta function as Celine introduced it on Monday. So the denominator being 1 minus t, 1 minus norm of pt. This holds for all p good, a prime of good reduction in the ring of integers, and it is independent of L, not equal to p. Okay, so what might we want to know about this linear algebra object? Well, we could ask lots of questions about it. We could ask precisely what is the image. This is packaging together the L division field, the field you get by joining the L torsion, the L squared torsion, and just kind of giving us something in characteristic 0 to work with, as opposed to those finite group questions that we might ask. But I don't know, a natural thing is how big is it? Is one thing that we might want to answer. And I don't mean like, is it surjective mod L? That's a different, that's an interesting question to study, but I want to think a little bit more broadly in this sense. So we might answer instead by what is the group that contains it inside GL2G. So let's phrase that in a linear algebraic group style of answer. Okay, so what's the linear algebraic group, the smallest one that contains this image of the group? So first of all, to make this as simple as possible, we replace TL with VL, where you tensor with QL. So now this is a 2G dimensional QL vector space, which is easier to work with. And we look at, now we can ask about the QL automorphisms. Bless you, I hope you're not allergic to Tate representation. That's a bad sign. Okay. Okay, so maybe choose a basis and think about this as an algebraic group over QL. I'll try to get it right between it. It's the points of the algebraic group or the group itself. But what you could do is to just take GAL. I'll lift this board in a second. Be the Zariski closure of the image. Okay, so this GAL is a reductive group. Over QL. And you really should think about it intuitively as I take all of my matrices, it's got coordinates, the affine space, the 2G by 2G coordinates, and I just think about that as a variety over QL over affine space, and I take the Zariski closure of that thing. It's a group, so by closure it retains the group theoretic properties, which is what we're going to be studying. And that's like, what are the equations in the coefficients of the matrices and the inverse of the determinant? What are all of those that vanish on the image? That's what we are trying to understand. It's called the L-adic monodromy group. This is somehow in analogy with the monodromy group over the complex numbers, thinking about this as being like a pi 1. Now you might, what should we expect typically for the answer to what is the L-adic monodromy group? Well, typically or usually, abelian varieties have big Galois image. They are principally polarized, or at least a polarization whose degree is coprime to L. And in that case, this GAL is GSP2G, so the full group. And that's what happens almost all of the time. Okay? We might be interested in what else are the possibilities, what can happen, and if you have that personality style, you want to know, what's the most exotic thing that you might be able to produce, or sort of how bad or how interesting can it get. So nobody promised that this reductive group was going to be connected. It's one of the first things that you learn in linear algebraic groups is it might be disconnected, and then you take the connected component. We've seen that a couple of times in the lectures this week. So let's think about the connected component. Is there an echo from the mic, or no? Okay, just in my head. And I'm going to write pi 0 of GAL to just be my abbreviation for the component group. Just sort of trying to signal the meaning of what this quotient is representing by calling it a pi 0. So this is a finite group over which which is quite different in nature than what you get from the connected component itself. It's some finite extension of our base field, and then the rest is going to be the infinite extension that is like your GL or GSPs for which the linear algebra applies. Okay, now what can we say? So far, everything we've defined, it looks like it depends on L. So in fact, it does not, just like we might be expecting from these characteristic polynomials being independent of L. So that's a theorem of Serre. So there exists a finite group which I'll call phi A. Sorry, that's not a very good phi. And a surjective group homomorphism so it's such that this map epsilon AL, which is the map from gal f to the pi 0 of GAL. I didn't mention this, but all of these objects retain the property that they have an action of Galois. So in particular, gal f acts on this. All right, so a priori it looks like that depends on L, but actually there's just one finite group, abstract finite group, that explains all of these L-adic component groups. So there's one group homomorphism from Galois group to phi A, such that this one factors through with a canonical isomorphism from phi A to the phi 0 GAL. So this finite group is kind of canonically isomorphic to phi A, and the morphism that looked like it depended on L just came from a morphism that is independent of L together with an appropriate identification. Okay? So what does that mean? That means now we can talk about a number field extension that's independent of L. So let's let that be f epsilon A. So this is inside the algebraic closure. Sometimes this field is also called FA con. I guess it's trying to remind you that it's about the connected component of the L-adic monodromy groups. I like to think about it this way. If you had a character, we always write q chi to indicate that I join the values of chi. It's like the minimal splitting field of this group homomorphism. So that's why I denote it like this. B, the field extension of F cut out by epsilon A. So I've got my F. I've got the field where I join the L infinity torsion, always inside an algebraic closure. The Galois group of this is the image of rho AL. And we saw that that is some subgroup of this reductive group GAL. And inside of here, I have a group field extension, which I'll call L maybe. And the Galois group here is phi A.
This phi A depends on F, right? Or
it depends on A, which was defined over F.
yes.
Absolutely.
So if you change F, this will also change.
That's right. That's right. And if you stay away from L, then it won't change. But if you go in between L and F, then it will shrink. Exactly. So this F epsilon A is the minimal extension over which these L-adic monodromy groups for all L become connected. So that is the reason that we might be interested in it. All right, I feel like you guys are hopefully nodding, but we should do the example of elliptic curves to kind of get a sense of what's going on. So what happens for elliptic curves? There are three possibilities. So first, this is the comment that I made about most of the time. So this is when E is non-CM. And in that case, the GEL is GSP2, which is also just GL2 of QL. There's not a lot more to gain from this perspective than just taking your representation with 2 by 2 matrices in the first place. Okay? Now you might think that the other option is CM, but in fact the CM comes in 2 flavors. Either the CM is defined over your field or it's not. And that probably makes a difference for this type of sensitive question. So we say E could be CM. Okay, and it has CM by a field. I'm used the symbol M for the CM. It's the multiplication field. Okay, and for an elliptic curve, that is a field of the form, Q root D, where D is a negative integer. And what do you get there? Well, then this VL of E is isomorphic to M tensor over Q with QL. So this ostensibly 2-dimensional QL vector space actually can be understood as coming from M itself. It's a 1-dimensional, maybe ML vector space. And that means that the endomorphisms, which are defined over F, commute with the Galois action. So the image is not nearly as big as GL2. All you have to do is to rescale by these elements of M. Okay, so this means that GEL is isomorphic to GL1 over this ML. Okay, smaller. Yeah, when I say CM, I mean it has complex multiplication. So over F. I'm trying to get us to say that all, maybe my agenda isn't clear by making it feel like this is inevitably the definition, but I believe that when we say an object has an endomorphism, it is not that it's defined over the algebraic closure, it's something that should be defined over the ground field. So when I say E has CM, I mean over F. Okay, and then what do you say if it's not? Then you say it has PCM. Sorry, do I sound grumpy? A lot of my conversations end up in this world where we have to distinguish between the field of definition. And that's exactly what we wanted to study anyway, okay? So it has potential complex multiplication. And in that case, E obtains CM over some other field. What is that field? Well, let's see, M is like the field of endomorphism, so it's like a quadratic field, and then it obtains it over a field which maybe I'll call K, and K is Fm. That's kind of an accident of elliptic curves, that the endomorphisms are also defined over the extension, which happens to also be the CM field, and that's not always the case in higher dimension, but I hope I'm making sense. Okay. And this is where GEL is disconnected. The size of this component group is 2. What is the extension that you need to go here? This L actually is equal to K. You have to go up to a quadratic extension in order to see the property that is defined in the previous bullet. Okay, so what does that look like in terms of the matrices? Well, they're not all contained inside this AB minus BA style group. They're not yet always given by the elements of M. There's an index 2 subgroup with that property. And what's the larger group look like? Well, it's the normalizer of that inside GL2. Okay, so there's like this other half of the matrices that have some sort of property. Do you guys like Sato-Tate groups? You can also see that in the pictures where we're expecting a dome, but actually for these PCM cases, there's the dome and then a point mass at the origin. And the fact that it looks like it's the union of those two pictures is exactly measured by this connected component. Okay, so what did we just discover in thinking about elliptic curves? Well, we saw our first disconnected L-adic monodromy group, but it was kind of just explained by endomorphisms. Okay, so let's talk about that for a second. In general, that was in the example we had a K. So let K be the field over which the endomorphisms are defined. Same kind of symbol. I have a end A, which is a group scheme, a ring scheme, in fact. And then there's some place where all of them, a minimal extension over which the points of this is defined. So I define it, sometimes called the endomorphism field. I resisted this name for a long time because endomorphisms don't always make a field. So you have to read the field over which the endomorphisms are defined. It's too late, that ship has sailed. That's what people say. This is the minimal extension over which the geometric endomorphism ring of A is defined. Okay? And then how do these two things relate to one another? Well, there's a theorem of Silverberg, which says that how big can this endomorphism field be? Well, it's contained inside the M torsion for all m greater than or equal to 3. And once we're thinking about that, we might try to quantify our connected monodromy field. I didn't call that connected monodromy field. All right, so what about that? If we have this kind of containment, what happens here? This is a theorem of Larson and Pink. This f epsilon of A is contained inside the intersection over all L of the field that you get by adjoining all L to the infinity torsion points. If you didn't like this description in terms of Galois groups, I invite you to tune back in and just take this to be your equals. It's contained in, and in fact, it's equals. So you can take this as the definition of the connected monodromy field. Does that make it seem like a natural thing to be studied if I hadn't convinced you otherwise? You take the 2 to the infinity torsion field, the 3 to the infinity torsion field, 5, and you say, is there anything that's in all of those fields all the time? If you like to think about entanglement of elliptic curves, apparently the theorem is that there's only this style of entanglement where you go all the way up the L infinity towers when you have Cm. But we're going to be interested in higher dimensional situations. OK. Well, do you guys see a containment based on these two theorems? Hopefully the evident containment. Well, if this is already contained inside all the A to the m's, then it's certainly contained inside this intersection, which means it's contained inside here. Okay, so the endomorphism field is always in the connected monodromy field. Okay, and again, that's why maybe we'll call this thing K and this thing L, if we want to keep track of where the fields are. Should I put that in the diagram up here too? Might as well. Not enough room. Okay, so we've got some finite extension that always contains the field of definition of the endomorphisms, and then, of course, the question, which is attributed to Folklore. He does a lot for our community. He, they, OK, Folklore, question. Okay, so the question is it always the case that the connected monodromy, do you just have to go up to the field where the endomorphisms are defined, the sort of obvious sub-extension, or is there something interesting and exotic that might happen, an additional extension that you need to get things to be connected? Okay, and there's a theorem that says we have to look farther than elliptic curves, certainly. So I hope it's OK if I just say equality holds for g less than or equal to 3. This isn't so hard to prove once you set everything up. If there is going to be an example where these two fields are different, we at least need to look at a fourfold. OK, and just a quick reminder, these have got to be exotic style objects. You know, like most abelian varieties do not have endomorphisms in the first place. And this is like, even if they have endomorphisms, can there be something else that happens? OK, and then here's our theorem. This is the main result of the talk. So for all even integers g greater or equal to 4, there exist infinitely many geometrically non-isogynous abelian varieties A over Q with dimension G. And these fields strictly contained. Okay, you are stunned into silence, processing. Yes, please. Oh, am I going to tell you more than you want to know about these guys? Yeah, thank you for inviting me to do so. Okay, I mean, I haven't gotten to say quaternions except in the title, so you know they're coming. All right, so it's better than the existence result. I'll write down an explicit family for you and try to tell you as much as possible about them. I mean, once we get going, we just wanted to resolve all the conjectures that we could in front of us for that particular family. In particular, I'll tell you what these fields are, you know, where they're, how big the discrepancy is, and so on. Okay, great. Is there any other question? Okay. Well, how would you prove a theorem like this? Where would you look? When it's an existence theorem, you could say, look in a moduli space and try to take away, you know, no. Let's be explicit if we can. You know, thinking of Boss, let's imagine that we want to be as concrete as possible in answering this. Okay. So now I want to write down abelian varieties somehow for you. Okay. Well, Kamal gave a very inspiring mechanism by which we might start to write down explicitly group laws for abelian surfaces. That was great. Okay, but we need a fourfold. Should we do that, Kamal? I don't. Okay. No. Let's write down a Jacobian of a family of curves. I think that's our best shot if we're going to be explicit about it. We have to get kind of lucky because, you know, most fourfolds are not Jacobians. But I remind you that these are kind of, you know, odd ducks, so that has a chance to work. Okay, so now I need families of Jacobians with some property. Okay, well, what property should they have? So there's a theorem of Murty, which I won't write down, but I'm just going to try to show you where we targeted these things. So the theorem of Murty says either you are type 3, if these two fields are different, either you're type 3 in the Albert classification, namely you have endomorphisms by a definite quaternion algebra over a totally real field, or your Hodge group is different than your Lefschetz group. Lefschetz is the centralizer of the image of the endomorphisms, and it's sort of like the only piece that we really can understand purely in terms of endomorphisms. And to prove in an explicit way that the Hodge and Lefschetz groups are not equal sounds daunting to say the least. Even what I understand in the, this is an example of the principle, like you work on things for a while, I wish I really understood that more than just what I've been able to do about it. So I think that means we should be looking at type 3. Now, I was going to look at quaternions anyway, you know, it's sort of, but now I feel like I've justified it. If you want exotic objects in mathematics, you need look no further than quaternion algebras. Okay, so now we have to get even luckier. Think about, all right, curves. How am I going to make endomorphisms on my Jacobians from a family of curves? Well, endomorphisms might not be realized in a simple way on the level of the curves, but let's just ask for more. Ask for automorphisms of the curve, then induce endomorphisms of the Jacobian. That's going to be as explicit as we could possibly be. And now I think that's, you know, if in the best of all possible worlds it all works, then we have our family. Okay. So let's try to write down curves whose automorphism group contains the quaternion group of order 8. So we have some theorems that characterize this, you know, with some attempt to be universal, but let me just write down. So first of all, I'm just going to show you the answer for genus 4. Our proof is a kind of elaborate specialization, spreading out, looking at generic points, and then doing an inductive argument to get from genus G to genus G plus 2. So somehow all the good stuff is already in genus 4. Okay, so for A in P1, you take away plus or minus 1 in infinity. We define the curve CA. Okay, so this is our, you know, even better, it's not a random genus 4 curve. In fact, it is even a hyperelliptic curve. This is for A not in this, then CA is a nice, so smooth projective geometrically integral curve of genus 4. You can also think about it as being parameterized by the parameter A, and we'll let AA be its Jacobian. And is it visible? So how did we come up with this family? Well, do you see the automorphisms? I hope you're kind of used to this. So there's an I, which acts on xy, just like it does in the elliptic curve case. And then there's a j, which acts by 1 over x I y over x to the 5th. Okay, so these give I and j in the automorphisms of CA defined over QI, and they generate Q8. So you're supposed to see I as having order 4, j as having order 4, and they skew commute, just like in the quaternions. So CA is universal. So we have, in other words, if there is ever a genus 4 curve equipped with an action by Q8 described this way in terms of differentials, then it has to be a twist of this family. So this, you could always take a quadratic twist of this family. So I have to somehow describe versally or whatever description of that stacky universal object. But that would be another way that you could think about this family. So we take inside the moduli space of genus 4 curves, there's a particular loci of curves with Q8. It turns out to be one-dimensional. It turns out to be, it's contained inside P1. And you can describe it very simply, once you know that it is hyperelliptic, to ask for polynomials with respect to differentials in a particular action. You end up with this family. So you could also interpret this as being a Shimura variety of abelian fourfolds with the endomorphisms generated by this ij. So it's a PEL type Shimura variety. And that's the thing I think Boss might want us to say. It's a miracle that abstract moduli functor is described by P1, and this is the family over that P1. I'm never in the situation where equations for moduli spaces or Shimura curves come quite sort of falling down in that kind of way. So this is really something. Okay, so as I said, the endomorphisms, the automorphisms of C give us endomorphisms of A, and so we get this O. Maybe I'll get rid of the brackets. It's not really clarifying anymore, I don't think. So this sits inside the endomorphisms of A defined over Qi. This is called the Lipschitz order. It might be the first quaternion order that you've ever seen. This is contained inside the quaternion algebra B, which is -1 over Q. Oh, I feel so much better now that we've got a quaternion algebra on the board. Okay, so we would say that AA has PQM. So it obtains a quaternionic multiplication over the field Qi. Okay. So what are we going to get? This is the family that we would like to see as realizing the difference between our connected monodromy group. And maybe you don't care about that anymore. You just want to see what we could say about this family of curves. All right, so let's do it. The first question you might ask is the endomorphism algebra or its ring any bigger? Or is this all there is, at least generically? Okay, so there's a motto that helps us to understand the answer to that, to answer that question. And the motto is endomorphisms wanna inject, wanna be in the Spice Girls kind of way, you know. They're not quite right, but the spirit and the enthusiasm is there, okay? So in order to understand the generic endomorphism, sort of thinking about A as being a parameter over the function field QA, what we should do is to just look at a particular fiber. This is the kind of thing you might do in a If you have a family of polynomials and you want to know its Galois group generically, you could get information about that first, a lower bound by, so to speak, by looking at a specialization. So that's the first computational step. So we picked a nice enough value, just the specialization at A equals 1/2. If you take that and you look at its geometric endomorphism ring, so that's the base change to Q bar, this is just O. So that means that the endomorphism field, this thing that I called K, is Qi. All right? So how do you prove something like that? I mean, I have an explicit equation for you now. Nothing exciting about this. This is x to the 4th plus x squared plus 1. You might write, if you asked to write a random hyperelliptic curve, you might end up with something not random, but nice and symmetric like that. So how do you ever compute an endomorphism like that? Well, there's a button that you can press. And there's an algorithm that I developed with Edgar Costa, Nicola Masco, and Jeroen Sijsling. All right? So I think for reasons of time, I won't go into this step because I'd be happy to tell you more about what goes on. But there's a little Magma terminal where you download our code from GitHub, and then you type the equation of this curve, and it describes completely the endomorphism algebra and the endomorphism ring. So what are the ingredients that it uses? Why did I make the Spice Girls reference? Well, there is a lower and upper bound, endomorphisms injecting. So there's another way that you can take this, which is the endomorphisms defined over Q inject into the endomorphisms defined over Fp, and similarly over the algebraic closure to the algebraic closure Fp bar. And then you can start reading things about the endomorphisms algebra, an upper bound, so to speak, by using Honda-Tate theory. So if I tell you the characteristic polynomial Frobenius, I've already told you a lot about the endomorphism ring. That gives you a container. And then how do you provide lower bounds? Well, you look at the associated complex lattice, you look at matrices that preserve that lattice, and then you exhibit the associated endomorphism by writing down a correspondence on the curve. So there are explicit equations that describe it. And in this case, we don't even need that because we already have exhibited enough endomorphisms. So we just need the upper bounds. So you look at p equals 41 and 83, I think, and that's all you need to conclude by the intersection that this is it. Okay, so as I mentioned, endomorphisms of the generic fiber inject into the special. This we already showed that this is only O. So that shows you that it's the endomorphisms of A, Al are just O. This is generically. There are specializations where the endomorphisms grow. That includes sort of places where the roots have additional symmetries. They're analogous to like CM points or something. Yes, please. Yes. Yes. Given by an equation. Yeah. Yeah. And how do we do it? Well, we need the period matrix. Magma can compute that, but yeah. Does not need to be hyperelliptic. That's right. Yeah. We can compute the period matrix for any curve. It's done via map to P1, looking at the monodromy of the branch locus, resolving the differentials, all that good stuff. Okay, and then, so we're on our way to identifying the abelian varieties in the theorem. I told you the lower bound K, and now I need to somehow exhibit a field extension L, which is going to be bigger than K. And here's the punchline for that. So generically, Q epsilon A, sorry for the double subscript, is Q zeta 8. Okay, so we have to do some, if I told you this generically, how do I get infinitely many geometrically non-isogenous one? There's like a height argument where once you know it's geometric, you ask yourself under what conditions something else could happen. And it's a very general approach that's almost like a Hilbertian property of the field. Once you know the generic Galois group is some group, it's not hard to exhibit specializations that it's that group. So that's how we get the infinitely many via the specializations here. So to finish the proof, I just need to explain to you where the Q zeta A comes from.
This is for this A?
It's A sub A, and it's this one.
Is that particular example?
Let's see. It's when I say generically, I mean A is taken to be in this P1 of Q.
No, but I mean, you are referring to the Jacobian of that curve.
Yes.
That particular curve.
Exactly.
Yeah. So you are not for any G. Right now you are in G.
That's correct. That's correct. And to show you genus 6, 8, and so on, we have kind of a deductive argument that does a degeneration. So in genus 6, there's a similarly defined family. In fact, you just repeat factors like this, but with A1, A2. And what we do is we degenerate those families to see the results that we need using an inductive argument starting at genus equal 4. And from that, we can bootstrap from this specific calculation. See, I'm only showing you genus 4 here. OK, so we prove any other questions? Again, we prove this by a specialization argument looking mod P, which I find kind of charming to do some. How do you see this discrepancy on the level of L polynomials? I'll try to make that as explicit as I can. The proof involves input from Banaszak and Kantorol-Farfan. Did I get the accent in the right place? Yeah. Okay. For the family AA, so they have a general statement that says if you have a type 3, a simple abelian surface, then, and it's fully of Lefschetz type, that's the hypothesis that you need. We have to verify that along the way, but I will ignore that hypothesis for now. Then the degree of L over K is at most 2. Okay, so somehow this Q zeta 8 being bigger than Q adjoint I shows that the upper bound that they prove using theoretical arguments, I'm about to show you where this 2 comes from, is indeed sharp. Okay, so they use work of Banaszak, Gajda, and Casson. Okay, so let's take our A is going to be some particular member of my family, and I'm just going to abbreviate it A so that I don't distract you with subscripts. So remember I have my VL of A. This is some 2 times 4 equals 8-dimensional QL vector space. But over QI, it has endomorphisms by O, and therefore endomorphism algebra, the quaternion algebra B is acting. So it's not just a QL vector space of dimension 8, but actually it's a free BL module of rank 2. Okay, so it's isomorphic to something with the BL action, and you can squeeze a little bit more out of this. So there's a thing you can write down which chooses a good basis for that rank 2 BL module. So, but you should think about this as being BL squared, a left BL module. Okay, so what's more is that the Voight pairing, A is a Jacobian, so has a principal polarization, and therefore a Voight pairing on it, a non-degenerate pairing. You can see what that pairing is giving you in terms of this BL basis. That's part of the choice here. So induced from the Voight pairing, you get a non-degenerate symmetric pairing on this WL of A. So it's a symmetric bilinear form. So it's psi L, WL cross WL to QL. So that gives you that this GAL, it has to preserve this pairing. So it's contained inside the general orthogonal group, the group of similarities. I'm allowed to rescale the pairing. So it lives inside this GO. Does it? Well, GO, so friendly reductive group, right? But there's a distinction between reflections and rotations, right? That really is the determinant of such of matrices when you look about O. There's really a plus or minus that is evident there. So it should not be surprising that there's the connected component of this, which is called GSO, and the connected component of this GAL is contained inside this GSO. It's like a kernel of the determinant which keeps track of the similitude character at the same time. Okay, so that is where an index 2 phenomenon occurs, and it's cut out by a character which we call omega L. Okay, so let me show you what this looks like if you play around with L polynomials. Yes, please. I don't think it matters for this construction. We could do so without loss of generality if we had to. Everything should be independent of L. Okay, so let's look at what happens for A equals 1/2, our specialization. So I'm going to take the prime of P13, which is generated by 2 plus 3i inside Zi. These are the primes over the Qi. So you can compute its L polynomial. I guess I have to base change to this FP. Okay, so this is a degree 8 polynomial that you get by counting points. So P13 has residue field size 13, came from a base change. So actually all I have to do is take my original family and look at the zeta polynomial, the L polynomial for P is equal to 13. That's a degree 8 polynomial. But over Qi, now that we have the space change, we see that actually it should be the square of something because I have the quaternionic anamorphism. So you see this the degree 8 polynomial actually is the square of a degree 4 polynomial. That's a common feature of when you have quaternionic multiplication. And this is what it looks like. So the 13 comes from the size of the residue field. It's squared because 13 to the 4th is what you expect. It's the q to the g when you think about the determinant of Frobenius acting on that space. Okay, so this polynomial factors in a certain way. And when you factor it, you get a minus sign here. That's how you take a degree 8 polynomial, you see degree, and in general, because when I square this out, I have to get 13 to the 4th t squared, I always have to have plus or minus 1 here, because it's the square of that polynomial. So this value here is the value of omega L if I take this rho AL frog P. T to the 4th, T to the 4th, T to the 4th, T to the 4th, T to the 4th. Thank you. Okay, and since this is minus 1, that already tells us that the image of the representation is not contained inside GSO. I found a Frobenius element which is not equal to 1, therefore the character has to be non-trivial. When I restrict to the Galois image, I found a Frobenius element that actually resolved it, and this is the proof that they are different. So how do you get that the field is actually Q zeta 8? Well, you establish that this character omega L is only ramified at primes of unstable reduction. So in particular, if you have good reduction at P, then the character has to be unramified there. So it's only ramified at semi-stable primes. Anyway, when you plug in A equals 1/2 into this family, where is it? Right here. You see the Jacobian has good reduction away from 2 and 3. So now I have a quadratic extension of Qi, which is unramified away from 2 and 3. So that gives me a finite list of possible quadratic extensions. I know that this prime is inert in that extension. And so there's like a Sherlock Holmes style argument where you line up your fields as the possible suspects. And then by doing a computation on this Frobenius, I know you cannot be the suspect. And in the end, there's only one suspect that remains, and therefore has to be the field. OK. So implies G L not equal to K. All right. So maybe I will just say in words what else I was going to write. So we proved infinitely many, but in fact, we did a lot more than what is written up here. Along the way, we can prove there's a density 1 subset of specializations A, for which the Jacobian AA here has the following great property. So it's endomorphism ring. Geometric endomorphism ring is the Lipschitz order. It's defined over Qi, so that's its endomorphism field. The connected monodromy field is Q zeta, across the whole family. It's explained by this character, which you can get your hands on. And we also show that for this density 1 subset, the Jacobian satisfies the Hodge conjecture, the Tate conjecture, and the Mumford-Tate conjecture. That kind of comes along for the ride once you've exhibited the cycles that you were expecting from the discrepancy between the connected monodromy field in the first place. And what is the Mumford-Tate group that comes out of it? Well, the Mumford-Tate group is a form of GSO4, because you see that from the description here, that the actual image is not in GL8. In fact, it sort of preserves quaternions, so it's in like 2 by 2 quaternion matrices, but even inside of that, there's a symmetric form that it has to preserve. So somehow the Galois representation, once you restrict to the Q zeta 8, it really is just inside GO4 of that CM extension. And one of my favorite parts about this argument is that although the VL of A is free of rank 2 over BL because BL is a division algebra, at least when B is a division algebra itself. So, that's sort of forced by the very nature of simple algebras. If you ask for the TL of A, which is this integral thing, it has an action by the Lipschitz order, tensor ZL, but it is not free of rank 2 over OL. And I'm at the end of the talk, so if I said that earlier on, you may have looked for the exits or something. I mean, what do you do with modules that are not free over your base ring, which is already non-commutative? You do run for the exits. What's going on? Why is that? Well, the Lipschitz order is not a maximal order. The maximal order inside this quaternion algebra is the Hurwitz order. You have to adjoin 1 plus I plus j plus k over 2. So it's analogous to a quadratic order that is not the maximal order. There are modules that are not free over that, and they're just free over the Hurwitz order. Okay? Now, that's not a bug of our presentation. There is a theorem of Shimura, which is an exercise in Birkehagen and Lange, that says that if this was free, then the Jacobian would have to split. We wouldn't have a simple fourfold. This would be split quaternion action, and then we would be sunk. Okay, so there's really kind of sensitive things that all line up to allow this family to have the properties that we needed. So we're lucky to have such a nice Shimura variety, and perhaps for that reason, we should try to apply the structure of this argument to other nice one-dimensional families of curves with additional automorphisms. So replace your Q8 by some other nice semi-direct product with a thing inside the group algebra. We tried to set up the argument in steps so that we should be able to get other very explicit nice families to help us understand Galois representations. Thank you very much for your attention.
Any questions? Yeah.
So, in the Rencontres case, what's the discrepancy between the degrees? It's always 2?
There's the discrepancy between the degrees.
Between the degree,
It's always the square.
it's always 2.
It's always 2, yeah.
Okay.
It is always, yeah. This general setup here, yeah, I guess this is specific to genus equal to 4. But in general, your polynomial is degree 2g, and it's the square of a degree g polynomial. I'm sorry that I got that wrong the first time, but that's where it comes in. And it is important that g is even. That's what allows this GSO to be a meaningful thing. So GSO for an odd dimensional quadratic space is not really a thing. You need a half of the, okay. That's where so 6 is even. Other hands. Yeah.
So you mentioned earlier about Hodge versus Lefschetz. Are these cases where Hodge equals Lefschetz?
Yes.
So
These are fully of Lefschetz type.
yeah, they're fully Lefschetz type. So is there some general statement about the L over K when Hodge equals Lefschetz? Is it bounded by 2?
Yes. It's 2 to the r, where r is the degree of the totally real field of the QM. So I bet, for example, we could make a bunch of z mod 2z to the r I mean, I won't have such a nice family for you, but one might expect that if you give it room, the Galois representation will provide and sort of fill in that space. Of course, we could also do that by taking products of these. Yeah?
I'm sorry if my question's a bit naive, but...
I love it. Yeah, please ask.
So I understood that your argument doesn't necessarily work in the odd dimension case, but is anything known in that case?
I think there are, in the odd dimensional case, because you can't be type 3, if there was going to be a discrepancy, but so type 3 means definite quaternion action, and then because you have to have module structures which 4 divides to G, and so then therefore G has to be even. That's sort of, at least if you want it to be simple, you didn't do something like take the product. I mean, I could do that. I could take this genus 4 curve with its Jacobian and then tack on an elliptic curve, you know, cross E. But that's probably not intrinsic to what's going on, if that makes sense. Okay, so then, yeah, in that odd dimensional case, you can't be type 3. So if there was going to be a difference between L and K, it's a theorem of Murty that there have to be a discrepancy between the Hodge group and the Lefschetz group, and that is something that is difficult to understand in a concrete way. So I will admit I don't know, I can't rule out something like that, but it would be much more exotic than even this. Does that answer your question?
Yes, thank you.
Okay. Yes, Alina.
Oh, I was curious about something. You kept saying how you got super lucky with everything sort of aligned properly, and these are all darks and exotic objects and stuff. Great. So how often does this happen?
Yeah, so my proposal is in the LMFDB, Jen Paulus has found, has isolated families of curves with extra automorphisms, higher genus. So we took another analogous family. It was a Z4 semi-direct Z3 kind of group, and started doing computations, and they look very similar.
So but we know, can you make your theorem sort of among the all,
Oh, sorry.
abelian varieties of dimension G, at least 4, how many of them would have discrepancy? Is that density 0? Maybe it's a very simple question. Is that like, if I have some sort of limit, what should I expect?
Well, if you look in the whole space of principally polarized abelian G-folds, then it's true, it's a theorem that the big image, big Galois image,
Okay, so
and so then it's GSP and then L equals K equals Q.
yeah.
So these are really like very high codimension loci inside that space.
So when it's quite amazing that you can find all these families, like you're telling me that there are all these things in a degree, that's quite...
Yes, that's right. So how do you combat how do you find something special inside a thing that is general? You ask for extra symmetries. So in this case, it comes from the automorphism of the curve, and you don't want to work with one of them, CM or something. You want a one-dimensional moduli space. So I believe that is the generality that you might hope from this construction, if that answers your question. Yes? Yes.
Yeah, so a bit refining, I mean, it's clear that now you have counterexamples to this whole core question. But you can refine it. You can ask, is there a bound in terms of the dimension of the given variety? Can we replace the equality by bounding units by some polynomial, let's say, some function of the dimension?
Yeah, you can use this Larson-Pink argument to understand the possible degree. It's not going to be a tight bound like Kedlai and Banizak thought very hard about what's the possible degree of the endomorphism field K over F. Guralnik, I'm sorry, thank you, Guralnik.
Yeah, so you can bound
really tight.
the degree of L over Q in terms of the dimension.
K over Q, the endomorphism field over.
No, we actually, we actually get about, our bound is actually on L, the degree of L over
Great.
So it just, as a corollary, it's bound.
So the first approximation to this, so read the paper, it's great. The first approximation is, inside these FA L infinity, what does that look like? Well, in the first step, it's going to be a GL 2G of FL, and beyond that, it's an L group. So if there is something interesting, the L is only going to appear, like what power of 2 can occur? Well, it can only occur in GL2 of FL for L not equal to 2. And then once you intersect 2 of those groups, that bounds. So that already intersecting any 2 of those gives you an upper bound on what the degree is. And that doesn't require any particular information. It just gives you a bound. How tight we can make that bound, I don't know. Well, at least we know that there are examples that are at least 2. And if you follow this to the limit, it'll only give you 2 to the something. So is there a case where L over K is not a power of 2? That's not something that we have the ability to test. But I think, is that what you're aiming at?
Yeah.
So a bound, and then how close can we get to that bound? At least we know it's not always 1. Yeah?
Have you been able to write other families for the quaternion algebra? That's not this one.
There is one that comes out of this other family that we looked at very briefly, the Z4 semidirect Z3. There you get like a -1, -3 quaternion algebra. But our method is to use automorphisms of a curve, and there just aren't that many finite groups. So you'd have to have your quaternions ending up in the group ring of that finite group. So we haven't investigated that question in general, but that's where I would look to see what else is out there. There was another hand. Yeah, Manami.
Yeah, so I was just wondering, all these examples, counter examples you are getting, for which, what kind of group this phi A, like in the shades theorem, appears? Like, is it like some finite list, or they can be like many different kind of groups? Do you know what
Yes,
phi A
yes.
is?
I would like to call these examples, not counter examples, if that's okay. Nobody's had a wrong theorem. We're showing that inequality is done, but it's all right. Is that an American thing to be unnecessarily positive about things? I don't know. Sorry, you guys. But okay. So phi A is a group of order 2.
Oh, always.
In our case.
And what about like if you
Sorry,
go
it's
higher in the genus?
yeah. That's right. If you go to higher genus, all we're able to manufacture are things that are coming from things like this character. So it's like GSO sitting inside GO, and maybe you have a couple copies of that because your quaternion algebra had several real places. Okay? So all I am getting are all we could get from this are multi-quadratic extensions describing the L over K. In fact, ours are even a little more boring than that. It's just zeta 8 over Qi for the entire family. So it's not like as you vary A, the L varies. It's constant over that whole family, sort of tied to the structure of it itself. So did that answer your question?
Yeah, so I was just thinking that if you want to make, is your theorem constructive for every genus? Okay, so you get a family for every genus, not just genus 4 or 6.
That's right, and it's very, I'm sorry you guys, I should have written down the polynomial so that you could see it, but it's like this, but you put A1, A2, A3. There's a description of the locus of hyperelliptic curves that have Q8 automorphisms to them. This is no longer universal for the moduli problem of abelian varieties, but it is still the universal family of curves. So as G goes up, each time you add an x to the 4th plus A2 x squared plus 1, the genus goes up by 2. Degree 4 becomes degree 2 for hyperelliptic. So we have more parameters as the family grows. That allows us to specialize genus 6, genus 8 to inductively bootstrap from genus 4. So they're as explicit as this in genus 4 for the families. And actually, a lot of our computations are very explicit with equations, and we're reducing mod prime. So we kind of need that in order for our argument to go. It's not acceptable.
Do you expect to build any other kind of families where the group PA would be different? Probably.
Yeah, Hodge and Lefschetz, that sounds hard. I don't know. Maybe we'll have to take that to the break.